Okay, let's get back into NP completeness. Yeah. Sure. So luckily for you, this is the hardest formula of all of them. So I think. Let me just check. Yeah, it's the hardest one. So what are we trying to say? We're trying to say that in this picture of what we want the machine to supposedly do, there's exactly one symbol in every cell. So like, for example, like I can't have a Q0 on that little blank as well. I have to have exactly one thing there. And of course I can't have nothing there. I need to have exactly one symbol there. So how do we accomplish that? Well, this must be true for every single cell, all the way through, all the way across, all the way down. So this outer and right here says it must be true for the top corner, then the second cell, then the third cell, then the fourth cell, all the way through, and every single row, every single cell. The inner formula must be true in order for phi cell to be true. So what does the inner formula say? So we're looking at one particular cell, ij, and we're saying that there must be exactly one symbol there. Then another way you can say that is there's at least one symbol there and at most one symbol there. So the first one, this giant or right here, says that there's at least one. Why? Because if none of them are set to true, so that means all of them are false, then this giant or must be what? False, because it's just false or false or false all the way through. So that, well, think about what happens here. This is and the other thing. So if it's false and anything, then the result is false for this cell, which means that the giant and outside must evaluate to false, right? So that must mean at least one of the variables in the middle is set to true. Because if all of them are false, then the entire thing is false. So here it just says at least one of these variables is set to true. Does that make sense? Well,
so like that's...
we'll think about it. So think of like x. Think of this. So if we have like these two, if there are, let's just say there are only two symbols, which they're not, but let's just say there are only two symbols, then could it be that both of these are false?
Yes.
It could be that they're false, but is phi sub cell true? Here. No, because this or right here, is that true? Just that or part right in the middle. False or false is? False, as far as I can remember. So let's just go on that. So this part right here is false, right? Then it says and something else. What is false and anything?
Could be false and false.
Well, what if it's false and true?
Could it be true?
So remember Boolean logic. If you have and, it's only true if both of the things are true. So then that must mean that this entire thing within the square brackets must be, so it's false and whatever. So the entire thing within the square brackets is false and anything is false. So the entire thing within the square brackets is false. So this giant and outside, whatever they were before, something, 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 and false and whatever. So the entire and is false. So I would recommend you to look over Boolean logic again. Yeah.
I'd like to clarify what the xij pound
Yeah.
means. So that notation means that we have a pound symbol at row 1, column 1.
That's what we want it to mean. It's just a variable name, so the formula doesn't know that, but that's what we want it to mean, yes. So in row I, column j, supposedly the value s is there.
When we set it to true.
Yeah, when we said it's true, yes. Yeah, but of course the formula doesn't know anything about that. But we're designing it to be that way. Other questions? I think you had one.
When you said that there cannot be another Q0, I don't understand why. Is it not a given that there will be something?
Well, it's because it's a formula. Any variable can be set to true or false, right? It's just a formula. So here, either of these could be set to false or true or any combination. Ignore phi sub cell for a moment. Any of them can be set to true or false. But phi cell, I still can set them any way I want. But phi cell is only true if and only if there's exactly one value everywhere in every cell. That's the only way phi sub cell could ever be true.
So there's only one that is either true or false that we can assign to it.
To a variable, yes. Okay, any other questions? Okay, so this tells us, so phi sub cell is just one of the 4, I think, formulas we're going to make. Phi sub cell just says there's exactly one cell everywhere. Great. Well, what else did we need to ensure that this computation runs successfully? Well, there are 3 things left to do. The first row has to start correctly, which means it starts Q0, W1 through Wn, and then blanks after. The last row must contain a Q except anywhere in the row, and every row must proceed via a transition, a valid transition of that machine from the previous one. Okay, so remember computation history, where we had a bunch of strings saying, this is the configuration now, then one step later it's this, then one step later it's this, then one step later. It's the exact same thing here. It follows from the previous one. So let's do the little formula that says we must start correctly. So i.e. the first row starts off with Q0, W1 through Wn at the beginning. So we're going to call that phi sub start, meaning it must start correctly. Okay, well, what does the very first row, first column have to be no matter what? The delimiter, £, yeah. So it must be that x1, 1, £, must be set to true, no matter what. And what does the second cell have to be? Q0. So, and x, so first row, second column with Q0 must be set to true. So remember, I still can set these true or false any way I want, but this formula that we're making will only be true if every single variable in this little formula is set to true. Okay, well, what must appear right after Q0? W1, then W2, then W3, etc. So x1, 3 with W1 must be there, and x1, 4, W2 must be there, then etc. And we go all the way through. And then what you'll find is that we end up with x1, n plus 2, although it's not really that important, the index. But we have Wn as the last thing. Well, okay, well, that's fine. But what must appear after the W string? Well, not immediately the £. A whole bunch of blanks and then the £. So we actually know how many. So then and x1, n plus 3, the next cell must be the blank symbol. Oops. And then it goes for a long way until we get to x1, p of n minus 1, still blank. And then the very last symbol, x1, p of n, is £. Okay? Does that make sense? So all this says is that this formula is true if every single variable in here sets true, because it's just a giant and all the way through. So it says the first cell must be pound sign, then Q0, then W, then a bunch of blanks until we hit the pound sign at the end. So this one is not too difficult. Any questions on it though? Yeah.
So without this one, we wouldn't have any real information
About where to start, yeah.
Where to start with anything, right? Because just with by cell, it's just saying.
There's exactly, yeah. So if I just had 5 cell, then if I just assigned anything to every cell, then that formula would be true.
Now, what if we had by start without by cell? Is that an issue? 'Cause
Then-
by start seems like it already has everything. One.
Yeah, if I just set all those variables to true and every other variable whatever, then the entire formula, then this formula is true. So the resulting formula that we're going to have at the very, very end is that it's going to be phi sub cell and phi sub start and the other two we're going to make. So it must be that every single one of them is true. Any questions other than that? Cool. So we have 2 things to go. So we have exactly one value everywhere. We had the first row start off correctly. Now we need to have the last row contain what? Q accept. Do I care what appears anywhere else? I don't care. So as long as Q accept appears anywhere in this string, we're all set. So how do I say this cell contains Q accept, or this cell contains Q accept, or this cell, or how do I say that? It's just a giant conjunction. Sorry, a giant disjunction, a giant or over all the column cells in the last row. So we're going to say, oops, can't draw my phi's today. Phi sub accept is just going to mean the last row contains Q accept anywhere. But that's just a giant or to say, oh, another thing. So we need to be a little bit careful on this one. Can the machine stop before the last row? Yeah, it could, because I guarantee it runs in at most this polynomial amount of time. Could it run shorter? Yeah. So could the Q accept appear taller or earlier in the, yeah. So I need to look at potentially every cell. So why not just look at every cell? If I can ensure that every row follows from the previous one via a transition, does it matter that I just look in every single place for Q accept if the machine follows correctly? No, so it actually doesn't matter. So we're just going to look over every single row and every single column, every cell, looking for a Q accept. So let's look for every row and column, and then just look for X, I, J, Q accept. So it's, this cell has it or this cell has it. If any cell at all has it, phi sub accept is true.
It happened before the last row. Would there be Q accepts afterwards too, so you could have multiple Q accepts?
Good question. It actually won't matter because as long as we can guarantee the rows follow correctly, then that means the machine accepts the input. So that means that the variables for the rows after, they can be set to whatever.
Okay.
Yeah. So that all we're doing is we're just putting an upper bound on how long it actually would take. But you're absolutely right, and we do need to think of things like that, where if it stops early, what happens afterward, like for the variables for the cells below where it stops, then we need to actually be careful and say they can be anything, because as long as we can guarantee the machine follows correctly every single row of the way, all the way down. Okay? Other questions? So the only thing we really need to do here is we need to ensure that every row follows from the preceding one via a transition. Okay, so that's what we're going to do with a formula called phi sum move. So here, we're not going to actually give the exact details because, of course, it depends on the machine. But let's think about what can happen. So suppose that we're looking at a particular row, and then we see some symbols A, B, and then some state Qi, doesn't matter what, and then some symbols afterward, and whatever. And then the next row, let's say that, so Qi is looking at what symbol? C, right? So let's say that it writes an E and moves left, for example. So the configuration after will be, in the state it goes as Qj, let's say. So A, Qj, since it moved left, is now looking at the B now. It wrote an E, and it looks like this. Okay? So that would be a possible transition of the machine. Of course, this is a non-deterministic machine. It could do other transitions, right? So it just happened to pick this particular one in this case. Question for you. What do you notice about here and here? They're the same. What about over here and over here? They're all the same. What about in this 2 by 3 box? This is where the action is, right? So this is what we're going to call a 2 by 3 window. Okay? Well, what do we want to know? We want to know is if we look at any 2 by 3 window anywhere in this machine, is it a legal window? So by legal, we mean either it's exactly the same as the row preceding it, or it followed from the transition of the machine. Okay? Because that's what it means for the next configuration to occur. It's either exactly the same as it was, or it changed around where the state was because of an actual transition. So we're not going to actually specify exactly what happens, but we're going to say that phi sum move is, we're going to look at all possible 2 by 3 windows and say, are you a legal window? If every single one of them is legal, meaning that it follows from a transition of the machine, or it's the same because it's not via a transition, then this whole formula must be true. So here we say that we're going to do a giant AND because we want every single window to be true or legal. Then we want, let's see. Okay, so I'm going to make it informal here. So for all possible 2 by 3 windows, it's called W. And then here it must be W is a legal window. Because if I want to define this in a very formal way, then I need to actually know what the transition function of the machine actually is. But of course, I don't know that in general. But I know I can make this formula based off of the transition function of the machine because it's a finite state machine. And so it has a finite number of transitions. And so therefore I can look and say, oh, now I know what the actual the actual transition actually looks like. And then I account for all possible windows that we can see. So for, like, say for that particular situation, that could be the result of one transition, or it could have written something else, or it could have been something else. So this little bit could be an OR over all possible transitions that could appear right there. But one of them that you can imagine is if you have a 2 by 3 window And the three things at the top are none of them contain states, then could a legal window be the exact same thing below? Yeah, because it could be that the transition function occurs way elsewhere in the two rows, and it just not happened to pick any of these two. Could, if the same situation occurred, so same three up here, but the third one over here is a different symbol, but is not a state, is this a legal window? No, this is not a legal window, because the only thing that could have happened is that the state was looking at that symbol and changed it to an A, but we assumed that it wasn't, right? And we know that this last thing is not a state either, so it couldn't have moved left. So this is not a legal window. So I take advantage of all possible legal windows that could appear, and then I just say, are you a legal window all the way through the entire tableau? So for every 2x3 window I could ever consider, is this particular one a legal one or not? Which means it must follow from the...
So if you have a 2x3 window,
Mhm.
but similarly to that one that happened on the other side, that could happen, right? Because the state could be...
Yes, very good point. So if I had... So remember, this is a legal window because it's the same top and bottom. What if I had this instead? This is a legal window. Consider if we look back and saw that a state was right there looking at that A and it moved left, changed it to a C. Could that happen? Yeah, so this is a legal window, but the one before with the ABA could not be. So we just look at all possible legal windows, and we'll be certain that it's a constant number because the size of the machine is constant relative to the input. Yeah.
So say like that situation happened, but it's on the leftmost input, like the input starts with A.
Yeah. So W will actually have to depend on what the indexes are. So I'm trying to keep this more of a high level thing, but of course if we want to make this more precise, then yeah, if we have W all the way butted against the left side, then a legal window can't have something different other than a pound sign in the left part, right? So if we're all the way against the end and we had a pound sign here and then an A afterward, that's not a legal window, right? Because we have to have a pound sign on the left side. But I want to keep this at a more high level. But yeah, you need to take care of things like that. Any question about what we're trying to do here? So let's just recap, and we're actually almost done. So believe it or not. So we wanted to say, we wanted to model the computation of the machine. And we knew how long the machine ran by assumption, and so we knew how far to go. Then we made variables for what can appear. We first said there's exactly one value in every cell everywhere. Then we must start in this starting configuration. Then there must be a queue except anywhere in the machine. And then 5 moves says that every row after a transition will yield the next row. So any possible transition of M can result in the next row. And then what we're going to finally do at the very end is say phi is phi sub cell and phi sub, what did I call them? Start and phi sub accept and phi sub move. And that's the formula we're making. So it must have one thing in every cell, it must start correctly, and the accept state must appear somewhere, and every row must be yielded from the previous one. Well, if this is true, that this formula is actually true, then that must mean there is an accepting computation of the machine on the input, because whatever the variables that are true, I can fill in the tableau with those values, right? And then I can see, oh yeah, that was the transition that occurred. Oh, that was the next transition, and then all the way through. And then at some point, I'll see CLIQUE because I have it say, and it must contain a CLIQUE somewhere. And every row must proceed via a transition. So in fact, this formula is true if and only if the machine accepts the input. Kind of cool. Are we done in showing that 3 sets NP hard? No. What else do I need to know about this reduction? Right. If I make this formula in, say, exponential time, does that show us NP hard? No, it shows nothing. So let's be sure that this formula is only polynomial size in the size of the input, which was n, remember. Well, let's see. How many variables am I making here? Well, there's polynomially many of them, and that's for every row, any column, and let's just say a constant number of symbols, because it's only on the machine, not the input. So it's a polynomial times a polynomial for the every row, every column, times a constant, but what is that at the end? It must be a polynomial. Well, now let's make sure we have the formula as a polynomial size too. Well, this outer one for phi sub cell, that has polynomially many ands on the outside. And the inside is only constant size because it only depends on the values, right? So it's only constant size times a polynomial is a polynomial. Great. Phi sub start, this only has polynomially many elements in it anyway, so that's polynomial size. Phi sub accept looks over all polynomially many possible rows and columns. Again, a polynomial. Phi sub move is a little less clear because any value can appear in any of the 6 entries here. So you can think, well, that's 6 to the power some value, right? And that could be an exponential, right? So if the number of symbols that appears here depends on the input size, then I could have potentially an exponential number of windows I could ever look at, and I need to keep those around. So why is this okay here?
Because it doesn't depend on the input size.
Right. There's only a constant number of symbols that could appear. So it's 6 to some constant at most, which is, again, a large constant, but it's a constant. But I'm looking over all possible windows of the machine, but there's only polynomially many of them. So a polynomial times a constant, a large one, still a polynomial. And then the final formula is just a polynomial with a polynomial, polynomial, polynomial. Oh, it's a polynomial in size. And so therefore, I have made this formula in polynomial time. Pretty cool. Any questions about this?
Is that two-step?
Yes. Actually, not really. It's very, 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 very close. Well, what kind of formulas are we looking at here? In conjunctive normal form, right? So if this formula is in conjunctive normal form, great. If not, maybe we can do something about it. Well, let's see. This one is actually, it's a giant and of a lot of ors and an and of other clauses. So it's in conjunctive normal form, pretty much. The only issue here is that it's not necessarily in 3 conjunctive normal form. So it's not 3 set. So, and we'll fix that. So if it has more than 3, we'll see how to fix that. Here is definitely in conjunctive normal form, because if you just treat each one of these as a clause of one element, then it's an and of clauses, and we're okay with that. Phi sub accept, you can think of as just a giant single clause, right? It's just a bunch of ors, so just put them into one big clause, and so therefore it's a clause. Here, phi sum move is a little more tricky, but the only issue we have here is that we're looking at all possible windows, but that just means that it must be that this cell is set to this, and this cell is set to this, and set to this, and set to this, and set to this, and set to that. So it's just an and of ands, but potentially with ors on the inside. But there's actually techniques that I won't go into, but you can actually rearrange ors and ands and get the exact same formula value at the end. So it's not really that important here, but in fact we can convert this into CNF pretty easily. So I claim that 3-sat is now NP hard. But the only issue is, of course, as I mentioned, the clauses themselves may have more than 3 values, right? We handled when it has 1 or 2 by just repeating the occurrence of that variable. But what if it has more? So let's say that it has, let's say, x1 or x2. These can be negated or not. I'm not assuming anything. So how can I convert this clause of size 4 into clauses of size 3? Well, let's see. How do we do this? Okay. Well, I want to retain the original formula's truth value. So I want to maybe add additional variables to this little formula here that do not impact the trueness of the formula. So no matter what I do to these new variables, it's not going to do anything to the original formula. So the way we're going to do it is think back to the earlier example I gave you about the unsatisfiable formula, where we had some variables and then I made one of them in another clause be the opposite. So that's kind of what we're going to do here. What we're going to do is we're going to break this up into 2 clauses of size 3. So x2, or now I'm going to add a new variable I'm going to call z. So this variable has never been seen before. Let's call it z. So I'm going to do a wrong thing first, and I want you to tell me why it's wrong. So I'm going to put z in the other one, or x3, or x4.
C could be false.
Well, if I set z to true, is this little formula true? Regardless of what the x1, x2, x3, x4 are, right? So make one of them negated. Okay? If z is true, for example, let's say z is true, then it doesn't matter what x1 and x2 are, right? What has to be true of x3 and x4 then? One of them must be true, right? But does that mean that it's true in the original one? x1 or x2 or x3 or x4? Yeah, the original one's true. And the same thing if z is false, right? That means that the original one's true also. Another thing that we need to be careful about. What if the original one was not true? All of 4 of them are false. Is this second one true? Could you make this true if all x1, 2, 3, and 4 are false? Well, if x1 is false, x2 is false, what must z be? True for the first clause. But what does that mean for the second clause? Yeah, but that's not possible. So that must mean the resulting one is also false. So in fact, I do have the exact same value, truth value, no matter what, by doing this. So if I have a clause of size n, then if I just repeat this procedure, I'm going to break it up into one clause of size 3 and then one of size n minus 1. Do it again, n minus 2, then n minus 3, and then I break it up until I have order n, let's say, because I don't remember the exact number, order n clauses of size 3. So in fact, I can convert any CNF formula into 3CNF. Any questions?
If x1 is true and z is true,
Well, if x1 is true and z is true, well, that's a good point. No, I'm saying that there must be a way to satisfy it. So, is there a way to satisfy it if I set x1 to true? Yeah, I can set z to false. So I'm not fixing z to a particular value here, or any value, or any variable for that matter. I'm just saying, is there a way to satisfy it? Yeah, and the truth value is the same across the two little formulas. Actually, only linear, but let's just say polynomial. So an added polynomial, bigger polynomial. Yep. Other questions? Okay, so that was long and arduous, I know. So let's try to, so now we can actually say that 3-sat is NP complete because we showed it was an NP before, and then now through this long reduction that it is NP hard as well. So let's just write this down. Well, what was one of those other NP problems that we talked about before? Yeah, the CLIQUE one. So we showed it was an NP before. What if we showed it was NP hard? Then it's NP complete by definition. So do you think we want to go through an arduous process like this again to show that CLIQUE is NP complete? Maybe I would, but most of you probably wouldn't. So what would be a better way to show that it's NP complete? Reduction, and do we have a problem to work with?
Yeah.
3-sat. So we can actually show that 3-sat poly reduces to CLIQUE. So remember, this is just instances K, G, and K, so such that G has a K clique. Yeah.
Why 3-sat and just not like all sat?
Or any set. So the reason for this is that the formula has a nice structure. And the fact that we can bound how many literals can appear in a single clause is actually quite important. If we wanted to consider 2-sat instead of 3-sat, 2-sat you can actually figure out is solvable in polynomial time. But 3-sat, we believe, is not. So 3 is actually the lowest we can go without going into polynomial time. Okay. But any other questions? I want to get at least one reduction in today. Okay, so what are we trying to do here? We're given an arbitrary 3-sat formula, and we want to convert it into a graph and an integer k, such that the formula is true if and only if the graph has a k clique. So if the formula is false, the resulting graph, whatever it is, does not have a k clique. And if it is true, then the graph does have a k clique. So it's just like a reduction from before. And we got to make sure it runs in polynomial time, but we'll handle that. So let's see. Let's look at this formula. I know it has a repeated variable. Sue me. So the way that, so I'm going to say it in a high level, but it'll be more intuitive as we go. The way that we're going to handle this is we're going to look at any two clauses, and if they have an occurrence of a variable in one and the other version of that variable in the other one. So say one of them is in the positive form in one and the negated form in the other, then they can't have the same truth value, right? Because if the first one's true, the other one must be false. If the first one's false, then the second one must be true. So what are we going to do here? So what we're going to do is this. So we're going to look at each of the variables. So we're going to make it general in a second. But we're going to make a graph in the following way. So I'm going to make the first clause as vertices on the left, and we're going to make the other clause vertices on the other side. Well, suppose that we're trying to make edges in this way. There would be no reason for one of the graph nodes over here on one of the clause. So these are called clause gadgets, by the way. There would be no reason to connect one to here because we want to make edges between clauses that forbid. We want to make edges that are compatible. So if an edge is not present between two clause gadgets, then that must mean that those are variables of an opposite orientation of whether it's positive or negative. So, and it doesn't make sense to connect one variable node to another one in the same clause gadget. Okay? Because all we need is that one of them be set to true, and we don't need any more than that. Okay, well here we're just going to connect across the two gadgets, and the only ones that we're not going to connect if one of the endpoints is in the positive form and the other one is in the negated form. If they're the same, then that's okay, but if they're different, one's positive, one's negative, don't connect them up. So should I connect this x1 on the left to the x1 bar on the right? No. But what about the x1 with the x2 bar? Yeah, because I said that that's okay. So I'm going to connect it up to all choices. And I'm going to do the same thing here with the x1 here. And then the x2 on the left can't be connected with anything other than the x1 bar upstairs. Okay. Does this graph have a 2-clique? Meaning, does it have an edge? Yep. Yes, clearly. So let's make it a little bit more interesting. Let's add the clause x1 bar or x2 or x2. So again, I'm going to have another graph little gadget down here. And I got to connect it up everywhere to all the other clause gadgets. So if it matches, then that's okay. So the x1 down here matches with the x1 up here and with the other two as well. I can't connect the x1 bar bottom on the bottom gadget with the x1's positive on the left, but I can with the x2 over here. The x2s are similar, but I'm just going to draw the edges, although it's not, I don't actually need to at this point. And then this one up here. With these ones also, but so I guess the picture's looking a little horrible. So here's the thing. There are 3 clauses here. Is there a 3-clique anywhere? So a triangle. In fact, I'll point one out to you. There are actually other ones than this one, but here's one. So there's a triangle. What kind of property about that triangle do you notice?
Maybe true.
Well, in fact, stepping back from that, are any of the two nodes in this triangle in the same clause gadget? Or are they all in different ones? They're in all different ones. That's kind of interesting. So they're in all different ones, but doesn't that mean that if I pick the x2 on the left one, so that I pick this triangle, the x2 corresponds to the first clause, so I'm going to highlight it here. The x1 bar on the left corresponds to the second clause, and the x1 bar on the bottom corresponds to the third clause. Is that a satisfying assignment? Setting x2 to true and x1 bar to false? So this formula is satisfiable, and we found a 3-clique. So why could we do this? Because so we're going to make each one of these clause gadgets for each of the clauses in the formula. And we're not going to have any edges between vertices of the same clause, because we don't want to have this issue of I'm going to have k clauses at the end. Sorry, I start with k clauses, and I don't want to have to pick two vertices in the same clause, because I might leave a clause out, and then the formula still might not be satisfiable. So if I pick a literal in each of the clauses, and they're not incompatible with each other, that means I have a k-clique at the end. Interesting. Well, let's go back to our earlier example. If I go all the way up here. Let's do our unsatisfiable. Would this even work? Actually, it needs to be in 3CNF. So it actually would look horrible. But I claim that there wouldn't be a 4-clique in that one because it has 4 clauses. Okay? It might have 3 cliques in it, but it won't have a single 4-clique in it because it's unsatisfiable. So how do we do this in general? So suppose that the formula looks like this. So it looks like A1 or B1 or C1, and let's say that there are k clauses. And I know it's in 3CNF, so we're okay there. So we're going to make a graph G with vertices A1, B1, C1, etc., AK, BK, CK. And edges, and all edges present except those with the same index. So, meaning it's in the same clause. That's what I mean by that. And any 2 literals of the form x and x bar. So the edge here represents this. Each of these 2 endpoints are compatible with God, can't speak. The 2 endpoints are compatible with each other with respect to the satisfying assignment. So if one of them is set to a particular value, then the other one is either the same or it can be set independently of the other variable. And so therefore it's okay. If I made an edge between x and x bar, if I set x to be true, then it implies something about the other one, which means that's not exactly what we want out of a k-clique. Remember, the way that a clique could ever form here is since the edges go across between the clause gadgets, I must pick at least one vertex out of every one of the k gadgets, right? I must pick at least one. But if I said that this graph has a k clique, that means I must pick at most k things. Okay? If it has a k clique, I can't pick more than k vertices. I must pick at no, I can't pick fewer than k vertices. So let's see. So we start with phi, and then we do this reduction. We get the graph G that we just made, and the integer k, which is the number of clauses in the original formula. Okay? So let's see. So why is it true? The way that the k-clique could ever form, it goes across the clause gadgets, and since it goes across, that means we must pick a vertex out of each of them. But since all of them are compatible with each other, that must mean that since they're compatible, they are okay with the satisfying assignment. And so therefore there must be a satisfying assignment. Because I picked one literal out of every clause, and we can just pick that as the so-called witness of that clause to be true. Okay? Any questions? Yeah.
So if there was a clique with a k clique with one of the clauses missing, that means that it's not a clique, right?
Well, what do you mean one of the clauses missing? Like if you had this picture and you deleted that row at the bottom, is that what you mean?
No, I mean if you have like a clique in that, but only say like with x1 with like only two of the sets, two of three sets, rather than if you excluded.
Well, I'm making this graph based on the formula that's given to me. It's not an arbitrary graph that I'm given. I'm given the formula and I'm making the graph. Yeah, so it's based on the formula. Yeah. Other questions? Well, what is one thing we have to check about this formula? I mean, the graph we made. Polynomial time. So how many vertices do I have? Well, if there are k clauses, I have 3k variables, 3k vertices, because I make a vertex for each one of the literals all the way through. Well, it could be that every single edge all the way for any pair is present. So how many could that be? Well, it's at most the number of vertices squared, which means that it's polynomial in the size of the input, because it's just the number of vertices squared at most. And so therefore, this reduction works in polynomial time. So what can I conclude about clique? It's NP complete, because, well, we just showed it's NP hard, and we showed already that it's in NP. So from this, we can say that clique is NP complete. Any questions about that? Yeah.
Did you say it's NP hard and what else?
We showed it was an NP last time. And so therefore it must be NP complete by definition.
So to find NP complete, you have to show that it's an NP and NP hard?
Yes, by definition. Mm-hmm. Okay, so there's absolutely no way I'm going to do this next one in 2 minutes, but I'm just going to introduce it very quickly, and then we'll get right to it on Wednesday. So another problem, so cliques are important in my research for reasons I can get into, but another problem that's important in graph research, not necessarily mine, is I'm sure most of you have heard of the traveling salesman problem, right? Finding the least cost tour of a particular directed graph such that you never repeat a vertex, right? And so that's one problem, but we're going to make it a little easier here by saying that all the costs are the same. So here, that's what's called a Hamiltonian path. So a Hamiltonian path is one that visits every vertex exactly once. And we're going to define ham path to be almost the same as CLIQUE. Oh, no, sorry. Never mind. So it's just graphs G such that G has a Hamiltonian path. And then what we'll do next time is show, so first off, is ham path a member of NP? Yeah, so what would be a certificate here? The actual path. We would just need to check, is each edge an actual edge in the actual graph? And then if we just say, oh, is it actually a path? And it goes all the way through, then we can check whether or not it's an ham path or not. And then we'll show, so this is an NP, and then we'll show next time that it's NP hard. And so therefore it's NP complete. So I'll see you on Wednesday.